Hello everyone, welcome to lecture 11, normalization to third normal form. In this lecture we shall look at how we perform normalization on relations, and so we shall start with normalization to third normal form, where we shall look at data redundancy, functional dependencies, normal form, first, second and third normal forms, redundancy and normalization. A redundant data can be determined by other forms of data, uh, by other data present in the database. Generally, redundancy means repetition of data, and when data repeats in the database, it can lead to problems like insert anomalies, update anomalies, delete anomalies. You should know that an anomaly means a deviation from what is normal, right? Means that So it means that insert anomaly will simply mean a deviation from how insert normally functions. Let's say you want to insert a particular row, and then you do the insertion and it doesn't insert all what you have to insert, or you want to modify an element and then it modifies two tuples, or you want to delete an element and it deletes another you want to delete maybe a tuple, it deletes an element which was not intended to be deleted. Those are anomalies that can be caused due to redundancy of data, and that is the main goal of our of this core of this topic, normalization. It aims to reduce this normalization of this redundancy of data. Now, redundancy is expressed in terms of dependencies, and normal forms are defined that they do not have certain types of dependencies, right? Now, there are three types of normal form. We should start with the first normal form. Most relational data models define first normal form as data values which are atomic, and the entries should have that is the entry should have only single values and not composite values. In legal terms, we could say a relation is said to be in first normal form if all the values are atomic. For example, let us see normalization to the first normal form. We can convert an a on look at this table. We have two tables. We have the unnormalized table and the normalized table. We can convert this unnormalized table to the first normal form by changing these composite values to atomic values. No, that's an atomic value. Now we'll just have to produce another relation. Maybe we'll call the relation first normal form, having the same scheme, the scheme which is the set of attributes that define the various columns: module, department, lecturer and text. We'll start with the first tuple, m1 d1 l1 t1 t2. Now you see that in the column text we have a composite value, the t1 t2, and that's what we're going to change. So we'll maintain the tuple m1 d1 l1. We take the very first value t1, we put, we maintain the same entries for the first three attributes m1 d1 l1. I'll take the next composite value, which is t2. The same principle follows for the rest, and we'll obtain this table. So we see this table has been normalized to the first form. Some of the problems we observed in the first in normalizing to the first form is that we have insert anomalies, and in this normal point we notice that we cannot add a module. Let's say we add m1, we'll be forced to add text, so we cannot add module without the text. The next anomaly is update anomalies. For example, if we want to change the lecturer for m1, this is m1. If we want to change the lecturer for m1, you see that here we'll change the lecturer here, but m1 is also here, so we'll be forced to change the lecturer also here. That means we're going to modify two rows instead of modifying one row as initially intended. We have the delete anomalies. if we remove M3, if we decide to delete this module M3, is going to delete M3 alongside all the elements in its tuple, right? Now, but you notice that we do not want to delete a lecturer L2, but we are going to delete L2 as well. So those are some of the anomalies which you observe. Functional dependencies. Redundancies are caused by functional dependency. A functional dependency actually is a link between two sets of attributes in a particular relation, and we can always normalize these relations by removing undesirable functional dependency. Now let us say a set A mapped to B. This is read as what? It is read as A functionally determines another set B, or we could say there exists a functional dependency between A and B, and there will exist a functional dependency between A and B if whenever two rows of the relation have the same values for all attributes in A, and they also have the same values for all attributes in B. What do we mean by that? Now take a look at this example. We have attributes ID first, last, mode code, mode name. That's like module code, module name. Now the function, we say here that this set of attributes, there is a functional dependency existing between this set of attributes and this set of attributes, right? Or we say ID mode code functionally depends on first, last, mode name, and this will happen if whenever two rows of the relation have the same values for all attributes in A. Now let's say A is what? This first is A, right? ID and mode code, ID and mode code. If we have two tuples having the same ID and the same mode code, it will have the first, last name and mode name will be the same for those two attributes. So that's what it means by functional dependency. Functional dependencies and normalization. Now we define a set of normal forms. First, we can say each normal form has fewer functional dependency than the last one, and since functional dependencies represent redundancy, we can equally say that each normal form will have less redundancy than the last form. Now, not all functional dependency cause problems. So we shall identify the various sorts of functional dependencies that do cause problems, and we see for each normal form, we see how we can remove the type of functional dependencies that are a problem. And we shall also see we also need to find a way to remove all functional dependencies, because once we remove the functional dependency, that's how the normalization increases. Properties of functional dependencies. In any relation, the primary key of a functional dependency is a set of attributes in that relation. Now let's see the primary key functionally depends on a set of attribute X. What does that mean? We see that X here is the primary key, K is the primary key, and X is the set of attributes. Now if the primary key K functionally depends on the set of attribute X, it means that for every value of the primary key, a unique set of values for X is assigned to that value. And the same thing happens for candidate key. We all know that candidate key and primary keys are similar, except for the fact that primary keys are activated in a particular relation to show the difference, to be activated as unique. Any set of attributes, for any set of attributes, a functional, that is, for any set of attributes, X is functionally dependent on itself. Rules of functional dependency. There are three main rules of functional dependencies. We have reflexibility, augmentation, and transitivity. Reflexivity. If B is a subset of A, then we say that A functionally depends on B. And augmentation, if A functionally depends on B, we can say A union C functionally depends on B union C. We shall look at this just shortly. Transitivity, if A functionally depends on B and B functionally depends on C, then A functionally depends on C. For now, let's see examples of functional dependencies. Given the relation normalized to the first normal form, which we just did above, we observe here that the primary key is module text. Let's say the primary key is module text, right? They set module and text, that's m1 t1 as primary key because it's going to be unique for every value. We have m1 t2, it doesn't repeat itself again. So we will notice here that module text functionally depends on department lecturer. It means that if we have m1 t1, the values which will be assigned to it must be d1 and l1 for every m1 t1 occurring together. There are some trivial functional dependencies, like we have text and department, which functionally depends on the text. We equally have module, which functionally depends on itself, that it maps on itself, one of the trivial characteristics of functional dependencies. Then department lecturer, which functionally depends on no attributes. Functional dependency example. Okay, we're still using this same example, but we will also notice that there are other functional dependencies here, like module, which module functional depends on lecturer, module functional depends on department, lecturer functional depends on department, and these are all non-trivial determinants. That is the left hand side of the dependency are not keys. That is, module is not a key, lecturer is not a key. So we see that they are trivial, they are non-trivial and determinant. Partial functional dependency and second normal form. Now we shall define what partial functional dependency is, and we see how we can use it inside the second normal form. So a functional dependency A mapped to B is a partial functional dependency if some attributes of A can be removed and the functional dependency will still hold. Formally, there are some proper subsets of A. For example, we can say C is a subset of A such that C functionally depends on B. Let's call some attributes. Now let's call attributes which are part of some candidate key. The key attributes are and the rest are known key attributes. Second normal form. Now a relation is in second normal form if it is in first normal form and no known key attribute is partially dependent on a candidate key. We say what it is a relation is in second normal form if it is first in the first normal form and no known key attribute is partially dependent on the candidate key. In other words, we can say no C is functionally dependent on B, where C is strictly the subset of the candidate key and B is a known key attribute. Now let's see how we can actually form second normal form. We observe here on this table it has been normalized to the first normal form, and it is not, we have to know that this is not in the second normal form. So that is why we have, how do we know that it's not in the second normal form? Because we have functional dependencies, like look at module text which functionally depends on lecturer department. But also, right, but also we have module, which functionally depends on lecturer and department, right? So if we have module here, lecturer, department, they must be the same. For every module, the lecturer and the department must be the same, right? Module 1, lecturer and department must be the same. Let's say module 2, module 2, lecturer, department, module 2, lecturer, department, module 4, lecturer, department, module 4, lecturer, department. They are all the same. So this is another this is a sub dependency from the main dependency that makes it not to be in the second normal form. So our goal is to eliminate this dependency. If we eliminate this dependency, we take this table to its second normal form. So let's see how we can remove dependencies. Suppose we have a relation R with scheme S. Now when we talk of, let's say this is the relation first normal form, the scheme S is the set of attributes which form the columns in that table. Now suppose we have a relation R with scheme S and a function, and A functional depends on B, where A intersection B is an empty set, and let also assume that C is the difference between the scheme and the union between A and B. In other words, we say A are the attributes of the left hand side and B are the attributes of the right hand side, while C are all the other attributes. It turns out that we can split R into two parts. R will have a scheme of C union B, and R2 will have a scheme of A union B. The original relation can be recovered by performing a natural join between R1 and R2. That is, R will be equal to R1 natural join R2. Now let us see how we can split this and we obtain the second normal form. The first normal form is this relation we have to the right, and to split to the second normal form we'll have two tables. We can call it second normal form A and second normal form B. Now second normal form A, it's a projection of the first three columns, and the second normal form B is a projection of the of columns with attributes, module, and text. What do you observe in the projection of the first three columns? We see that wherever there's repetition, we could simply just write it once, like M1, M1, D1, D1, L1, L1. These two tuples are combined to just one, that is M1, D1, L1. The same thing, the same principle applies in M2. We write it just once, even though it repeats itself in the original normal form. M3 appears once, so write it. M2 appears twice, but we write it only once. And then M5. Now the projection of the tuple of the attributes, module, and text to have this new table, we see that text is unique for all values of M. So that is why, even though M1 repeats, but the fact that text is different, we write them each as different tuples. Now let us see the problems that this second normal form have resolved from the first normal form. In the first normal form, we had the problem that we could not add a module without with text, and we could not equally change a lecturer for M1 without modifying two rows. And if we delete maybe a module M3, we equally delete a lecturer L2, which was not the case. Now we notice in the second normal form that the first two problems are resolved, because now we can actually add a module without adding text, because the text attribute is absent in second normal form A relation. And again, we could change M1 without now modifying two rows, because we've combined the two rows to form just this single row. But the last problem is not solved, because if we remove M1, we are still going to remove L2, and and that's one of the problems which is still remaining. So let's see other problems which are remaining in the second normal form. We still have other insert anomalies, like if we want to add a lecturer, we cannot add a lecturer without adding maybe a teaching module to that lecturer. And update anomalies, like if we want to maybe change the department of L1, if we change the department of L1 and put maybe D3, we see that there's also L1 here, we'll be forced to equally change the department here and put maybe the same D3, and that is an anomaly. And the delete anomaly stays the same, because if we remove M3 we remove L2, which is not the initial goal. Transitive functional dependency and third normal form. Transitive functional dependencies and the third normal form. Now, a transitive functional dependency, a functional dependency A mapped to C is transitive if there is some set B such that A is mapped to B and B is mapped to C, and they are also non-trivial functional dependencies. Now, a dependency A mapped to B is said to be non-trivial if B is strictly a subset of A, and this therefore means that we have A mapped to B and B mapped to C, which means that A is mapped to A is mapped to C. Now, a relation is said to be in third normal form if it respects two conditions. First, if it is in second normal form, if it's already in second normal form, and again if there is no non-key attribute that is transitively dependent on a candidate key. Again, a relation is said to be in third normal form if first it is in second normal form, and if there is no non-key attribute that is transitively dependent on a candidate key. Now, let's look at this table, and you observe some dependencies. Is this table is in second normal form? Yes, we just got it from above. It's a second normal form, but you observe here that we have two dependencies. The module is dependent on the lecturer, and the lecturer is dependent on the department. So there is this transitive relationship because the module will finally be dependent on the department, right? So you see the module is dependent on the lecturer, and the lecturer is dependent on the module, which means that the module is dependent on the department. That's a transitive relationship. Now, our goal is to eliminate this that transitivity. The best way to do that is to create two different tables, as we did above, where the first table will contain lecturer and the department. Here you observe that the lecturer is dependent on the department only, and there is no other dependency in this table. And in the third normal form B table, you see that the module is dependent on the lecturer and there is no other dependency. So that means that we have eliminated the transitivity dependence. Now let's see some of the problems which we've resolved by eliminating the transitivity dependence. These are the problems which we had in the second normal form. You see that at first we could not add lecturers who teach no modules, but given the fact that we now have this table in the third normal form, we are now able to add a lecturer who has no module, because the table consists only of lecturer and department. So we can add a lecturer who is teaching no module, and the lecturer just belongs to a certain department. Now, we could not update, that is, we could not change the department for lecturer 1 without altering two rows. But given this, we see that we have the ability to change the department for lecturer 1. We could change it right at this table without altering two rows. We just alter just department 1. The next anomaly we had was if we delete M3, we delete L2 equally. Now look at third normal form B table, right? Here we have this tuple M3. It is true that if we delete M3 from this tuple, we are going to delete L2. But remember, L2 is also present in this or in the third normal form A. So technically, L2 is still remains in the data, and we've not deleted the lecturer. Normalization and design. Normalization is related to database design. So the goal when you're designing your database, your goal is that it should be at least in the third normal form, and if it is not in the third normal form, you should try to revise your database. When you have a known third normal form in the database, first you identify the functional dependencies that are causing the problems, and then you think if they'll lead to any update, delete, or insert anomalies. If they will lead to that, you try to remove them. In our next lecture, we shall look more on normalization, things like lossless decomposition, and why our reduction to second normal form and third normal form is lossless. We shall equally look at the Boyce normal form, which is a higher form of normalization. It comes directly after the third normal form. It solves some other kinds of dependencies, which we shall look at, and we shall equally look how to denormalize a database. Normalization to the Boyce normal form. In this lecture, we shall look more on decomposition. First, we shall see a brief review of relational algebra, then lossless decomposition. We move forward to the Boyce normal form, then higher normal form, and finally denormalization. Normalization so far. We have seen the first normal form, in which we change all the data values to atomic values, and the second normal form, in addition to the first normal form, we ensure that no known key attribute was partially related or dependent on a candidate key. In the third normal form, we saw that in addition to the second normal form, no known key attribute depends transitively on a candidate key. Lossless decomposition. In lossless decomposition, we normalize a relation by using projections. For example, if we have a relation with attributes A, B, and C, and A is functionally dependent on B, then we can project it on AB and AC without losing any information. This is called lossless decomposition. Algebraically, it can be written as R equal to the projection of R on AB natural join the projection of R on AC. So it will look like this, right? Relational algebra reminder. Selection. Given a relation R with 4 attributes A, B, C, and D, and this relation contains 5 tuples. Now we can perform a selection on it. Now this is read as the selection from R where the attribute C is equal to the attribute D. So we come on the relation R, we look at the two attributes C and D, and we check for equality in these two columns. Now we come to the first tuple. There is equality, C equal to C. So we take the entire tuple and we put here as the first tuple in the resultant selection table. We continue to check for equality, D in no equality, A equality. So the third tuple is copied and place as the second tuple in the resultant relation. BC no equality, CD no equality. Cartesian product. Given two relations R1 and R2, each of which has two attributes AB and AC, we can perform the Cartesian product R1 by R2 and having a resultant relation of ABAC. Now, how do we perform the Cartesian product? It's quite simple. What you do is you take the first tuple, in the first relation, and you relate it with each of the tuples in the second relation. This is what I mean. 1x will go with 1w, 1x 1w first tuple, 1x 2v, 1x 2v second tuple, 1x 3u, 1x 3u third tuple. The same thing, we take the second tuple in R1, we relate it to each of the tuples in R2. So we have what? 2y 1w, 2y 2v, 2y 3u. That is the Cartesian product. While on the subject, let us see how we can translate SQL commands to relational algebra. Now, we have an SQL command: select AB from R1, R2, R3 where some property alpha holds. We can translate this into relational algebra like this, and it can be read as the projection of R1, R2, R3 on AB where a certain condition alpha holds. I take it over. The projection of R1, R2, R3 on AB where a certain condition alpha holds. Relational algebra natural join. R1 is natural join to 2. It can be written as the projection of R1 on ABC where R1 where the tuples A of R1 is equal to the tuple A of R2. Now we have here two relations, R1 and R2, each having two tuples, right? AB and AC respectively. Now the natural join of these two will be where this condition holds, right? Where the tuple A of R1 is equal to the tuple A of R2. Now, what do we mean? So first we have to perform the Cartesian product, which we just did above here, and now we have to now see A. Here there is 1, here there is 1, the condition holds here, so it means what? This tuple will be present in the resultant relation which we'll have for natural join. That is why we'll have what? 1 x xw, right? 1xw. We do not repeat A because we are eliminating redundancy. 1 2 1 3 no equality, 2 1 no equality, 2 2 equality. So we have here what? 2y 2v, right? Where A is equal to 2 and A is equal to 2. So at this level, this is going to work. So it will be what? 2yv. 2yv will be the next in the relation. So I have what? 2yv, and that is natural join in the algebraic form. When is decomposition lossless? Let's say we have a relation R where module is functionally dependent on lecturer, right? This relation R has three attributes: module, lecturer, and text. Now we have to remove the dependency. We have to remove the dependency because we see here that module is equally dependent on text. So we have two dependencies here. So the best way to remove this dependency is to have a projection, right? We are going to project R on module and lecturer, and equally project R on module and text. So it gives us two new relations, right? Where we have module lecturer, module text. Now, when we are projecting R on module and lecturer, we extract the two columns and we place them out. And when we perform the extraction, we will see that we'll notice here that we have what the very first tuples have the same data, and there is no need to repeat the data because that will be redundant. So we write it only once, that is dbs nza for module and lecturer respectively, and then we fill the rest of the tuple accordingly. Now, projection of R on module and text. You see that each of the elements in the tuples are different for each of them, and that is why we write the four tuples, all of it directly, because there is no data redundancy, and by performing this projection we equally eliminate the functional dependency between module, lecturer, and text. When decomposition is not lossless. Now, in this case, we have a relation R. We have a relation S with a table. We have a relation S with three attributes: first, last, and age. First, we observe here that there is no functional dependency existing in this relation. So even if we perform projections, there will be no loss, right? It is not lossless because there is no functional dependency existing between first, last, and age. Now let us perform a projection of S on first and last tuples, and we also have a projection on of S on the first and the H tuples, attributes rather. Sorry. So now we start with the table in the middle. That is a projection of S on the attributes first and last. We will simply extract the first two columns having first and last, and we'll form the table out of it. You see we have what? John Smith, John Brown, Mary Smith, Tom Brown. They are all different, so there is no need to really reduce any data. A projection on S first and H. You see that John, there is a John with H20, there is John with H30. It clearly signifies that these are two different persons having the same name, but it is not it doesn't cause redundancy, so it's quite okay to write them out. Mary, John, Mary and Tom. Now, still on the subject, when decomposition is not lossless, where there is no functional dependency, if we perform the natural join of the two tables which we just have above, that is the projection of S on first and last tuple, natural join the projection of S on the first and last tuple, is supposed to be natural on the first and H tuple, right? It's an error here. We will have something like this: first, last, and H, John Smith. When is decomposition not lossless? Now, if we perform the natural join of the first two tables which we just obtained above, right, of the projection of S on first and last attribute, and the projection of S on the first and H attribute. After performing a natural join, we observe the addition of two new tuples, John Smith H30, John Brown H20, which were not present in the original relation, right? You remember it has to give us the original relation, but they are not present in the original relation, so that is the problem. Now, the best way to eliminate this problem is not to perform the natural join, but to rather leave it in its projected form, right? So we just project S on the first and last attribute, and also project S on first and H attribute. When you perform the projection, you will notice that at the level of H we shall have John 20, John 20, and since they are repeating, we write it just once, eliminating the redundancy. We equally have John 30 here and John 30 here. We write it just once, eliminating the redundancy, and that brings our table to a great form. Example: given that we have a table representing orders in an online store, and each entry in the table represents an item on a particular order, this table contains attributes: order, product, customer, address, quality, quantity, unit, price. The primary key here is the set of attribute, order, and product. First, let us see the functional dependencies in. First, we establish the functional dependencies. Now, each order is for a single customer. That implies that order is functionally dependent on the customer. Each customer has a single address. That means that customer is functionally dependent on the address. Each product has a single price, which means product is functionally dependent on unit price. Now, from the functional dependencies of 1, that is order functionally dependent on customer and customer functionally dependent on address, we see that there is transitivity, which we can deduce that order is transitively dependent on address, which gives us order dependent on address. After having established our functional dependencies, we have to perform normalization. Since there is no data in the table currently, we'll move directly to the second normal form, because we will not know if the tuples are having composite data or not. So move to the second normal form. And the second normal form, in order to normalize it, we will have to ensure that there is no partial dependency on any candidate keys. Now, we observe some partial dependencies like order, which is functionally dependent on customer and address, product, which is equally dependent on the unit price. So in order to remove the first functional dependency, what we do is that to remove this dependency, order functionally dependent on customer and unit price, what we do is that we shall project on R1 the table order, customer, and address, right? So we'll have a table R1 called order, customer, and address, and we'll have another table R2 having the attributes order, product, quantity, and unit price. That's how we remove the first dependency. Now, R1 is in the second normal form, but there is still partial functional dependency in R2 because product is partially dependent on unit price, right? Now, to remove this functional dependency in R2, what we do is that we shall create another table R3 having the attributes product and unit price, and then the remaining attributes, that's order, product, and quantity, will be placed in R4. Now we shall normalize to the third normal form. Given that we have already normalized all the tables to second normal form, R3 now can be split into 3 relations: R1, R3, and R4, right? As we've established here, we see that R3 and R4 are in third normal form, but R1 has a transitive functional dependency because order is is related is functionally dependent on customer, and customer is functionally dependent on address, which implies that order is functionally dependent on address. So to solve this, what we do is that we project R1 to have two other tables, order and customer and address. That will solve that transitive functional dependency. Now, summarily, this normalization was done in this in the when it was in its first normal form. We had just one table having the attributes order, product, customer, address, quantity, unit, price. In the second to eliminate some of the dependencies that exist here, we created two projections. We created three projections: order, customer, address, product unit price, and order product quantity. There existed some dependencies in this, so to eliminate those dependencies, we further projected into these tables: product unit price, order product quantity, order customer and address. The stream relation. The stream relation. Consider a relation stream which stores information about times for various streams of courses. For example, labs for the first years. Each course has several streams, and only one stream of any course at all takes the place at any given time. Now, each student taking a course is assigned to a single stream for it, right? Now, take a look at this relation. We have this relation comes with three attributes: students, course, and time, with several tuples. Now the candidate keys here are a set student, course, and student time. From this relation, we can come out with the following dependencies. We will see that student course is dependent on time. Time is equally dependent on the course. Now, since all these attributes are key attributes, this stream is already in its third normal form, right? Because all the attributes here are involved inside the key. So we say that this stream is already in its third normal form. Now, but it has some anomalies, like there we have insert anomalies because you cannot add an empty stream, right? Yeah, we also have update anomalies. For example, if we want to change 12 to maybe 9, we'll have to modify two rows. We have delete anomalies. For example, if we want to delete Rebecca, we might have to delete a programming and 13, and that means that we'll have to remove an entire stream, and that is not our intention. This leads us to what we call Boyce normal form. Boyce normal form will help us alleviate these abnormalities. A relation is in Boyce normal form if for every functional dependency existing between A and B is contained in A, or A it contains a candidate key of the relation. In other words, every determinant in a non-trivial dependency is a super key. We shall look more on super key very shortly. You just have to know that it is basically the same as the third normal form, except that in the third normal form we only worry about a known key attribute, and if there is only one candidate key in the third normal form, then the Boyce normal form is the same as the third normal form. Stream is not in now this stream is not in the Boyce normal form because because time is functionally dependent on course, and it is equally non-trivial, and time does not contain a candidate key, right? Now, in order to convert this to the Boyce code normal form, you see we have student course time. We are going to project student course on the stream and equally project course and time on the stream to have two separate tables, student course and course and time. But we will notice that the stream has been converted into the Boyce code normal form, but we have lost the functional dependency that exists between student course and time, because right now we see here that student is dependent on the course, and here the course is dependent on the time. Decomposition properties. Lossless. We say data is not lost or created when splitting up relations. That one is we've seen. Now, dependency preservation. It is desirable that all functional dependencies are preserved when splitting up relations. Normalization to the third normal form is always lossless and the dependency is equally preserved. Normalization to the Boyce code normal form is lossless but may not preserve all dependencies, as we just seen in the previous example. There are several other higher normal forms, like we have the fourth normal form and the fifth normal form. But the fourth normal form here removes multi-value dependency, and the fifth normal form removes joint dependencies. But in this course, we shall end at the Boyce code normal form. Denormalization. The goal of normalizing data is to remove redundancy, solve, insert, update, and delete anomalies, and this makes it easier to maintain the information in the database. The only problem we have is that it leads to the creation of multiple tables, which will have to be joined back, and it can be expensive. So sometimes it is necessary to denormalize the relation. Now, you might want to denormalize a relation if the database speed is unacceptable, means that it is very slow. That in that case it will be necessary to denormalize, and then, or if you're going to have very few insert, update, and delete commands, you might want to denormalize. Or if there's going to be a lot of select command that involve joining of many tables, then it is great to denormalize directly. With that, we come to the end of normalization. If any other question, contact me.